Seminar. And Andrea is currently an assistant professor in the Department of Geography and Geology at the University of North Carolina at Wilmington. She received her undergraduate degree in her Bachelor of Science and her Master's in Geology from Dalhousie University. And she completed her PhD in Earth and Environmental Sciences at the University of Pennsylvania. Prior to beginning her current position as assistant professor at UNC Wilmington, she spent 3 years in the Department of Geology and Geophysics at Woods Hole Oceanographic Institution. So Andrea is going to enlighten us today about how she and her colleagues have developed an 8,000-year record of sea level rise for Florida. Thanks, Andrea.
Thanks, Cheryl. Okay, so I can't talk about sea level in North Carolina because it's against the law, and I'm foreign, and I don't want to get deported, and there's a number of reasons. So I've come to Florida to talk to you guys about sea level in Florida. And this is I'll talk to you today about some records we've been developing over the last probably 2 years. And we're going to look at 2 different sites in northern Florida. We're going to look at a site in northeast Florida, basically right smack dab on the border between Georgia and Florida. And we're going to look at a location in the panhandle of Florida. So hopefully this will go well. So sea level, right? It's where the water slaps up against the beaches or the rocks or the cliffs, right? But really it's way more complex than that, right? It involves things like eustatic sea level, isostatic effects, tectonic effects, local effects, thermal effects, steric changes. Okay, and so all these things are changing spatially and temporally throughout records. Okay, and so they're a lot more complex than just the water just lapping up at the beach. Okay, and so it's all these things we have to take in consideration in order to actually reconstruct sea level at any given location over any given time frame. And so how we do that is we look at relative sea level, right? So relative sea level in time and space. We use a time-dependent eustatic function, so the actual amount of water in the basin. Okay. Isostatic responses, so the total response of hydrodynamic or glacial loading on the continents, and that rebound process. We have tectonic. These can be local. These can be regional. It can be local faults. It can be large-scale continental activity. Right, so total isostatic effect of the tectonic process, then you have these local processes, which tend to be smaller scale and vary by site. So all these things are occurring at the same time, but all over different time scales, and only some of them are going to matter depending on the length of your record. Right, so long-term tectonic influence aren't really going to be necessary to take in consideration depending on the time scales you're looking at, and that's really important to understand. Okay, and things like ice melt, well, that's going to be pretty important, especially along the Atlantic coast of the U.S. Because as you go farther away from the glacial maximum, right, the center of the Laurentide ice sheet, you're actually going to have isostatic changes along the coast that go along with a latitudinal gradient as you go away from this massive ice dome. And so that's something we're actually also going to look at. So you have to think about ice melting, ocean atmospheric interactions, terrestrial water storage, ocean circulation, and also these density changes. We're going to focus mainly on this glacial isostatic impact. So in general, just I don't know how familiar people were with the topic of relative sea level. So if we were in location A, B, or C, and we were to actually model what would happen with land level versus sea level changes, okay, we could actually go through time 0 through time 5, where we're building up an ice sheet to a maximum point and then melting that ice sheet back away. Okay, and so if you're actually standing at level A, you would actually experience, right, a decrease in land level and then an increase in land level as you push down the crust and then let it rebound once the glacier was gone. On the contrary, in position C, you get the complete opposite effect, right? You're at a distal location from the ice bulge, okay? And so you're getting impacted by, you're basically not getting impacted by that isostatic effect. Okay, if you're at position B, you're on something called the forebulge, right? So you actually have the exact opposite reaction as underneath the ice sheet. So as the ice sheet builds up, all the mantle's actually pushed out underneath the crust next door, makes that bulge up, so you have actually land level rise and then sea level fall coming out of the ice age. Okay, and all that is important, especially along this coastline as you go from the north to south. You'll get a gradation in this feature, basically. You're either going to be, up in Maine and up in northern Canada. You're going to be in places that were underneath the ice sheet. In Delaware, you're going to be likely on that four-bulge peak. Okay, and then as you get down to here, we're kind of teetering on this position here. We're not sure how far south the four-bulge collapse is actually impacting. Okay, so that's one of the things I was looking at during this study. So we know that this is spatially variable, right? This means that you're going to have spatially and temporally variable sea level all over the globe. Okay, so you're going to have certain places where you just have sea level fall. You could have a rise and fall. Okay, there's going to be different sea level trends in different regions because of all these different components, and that sea level is complicated. Why do we need to know this? If you're in North Carolina, there's no such thing, so you don't need to know about it. But there is something that we think that sea level is accelerating. The rate of sea level rise is actually accelerating. We can only say sea level change in North Carolina, so I'll go with that. So the large range, but in this prediction process where we've started to predict what sea level is going to do in the next, say, 100 years, there's been a range, a really large range of projections, right? Going anywhere from less than 20 centimeters to over 2 meters. And I think the next iteration will be out, I think, by the end of this week with the IPCC AR5. And I think it's going to even potentially make it even more grave. I think we're going to push up this boundary a little bit more. But these projections are really only useful if we understand what's already happened. Okay, and so we have to understand a geologic component of the past in order to see if these projections are unique or not. Has this always been the way sea level was? Is this unique to the past 100 years? Did it happen 2,000 years ago already like this? Right, so are these changes we're seeing now actually unique to the context? Like, what's the context? Okay, so developing these geologic records provides context for what is potentially going to be predicted for the future. Okay, is what we're going to see unique. The other reason why reconstructing these paleo sea level, or developing these paleo sea level reconstructions, is because they actually fit a nice niche that we have a gap in the time scale of developing records. So it's creating this geologic context to compare the predictions. It spans a gap in the records that we already have, and it's also capable of something that some of the other tools are not, and that's this decadal to decimeter scale resolution you can actually get. So it's a very high resolution technique that spans quite a bit of geologic time. Okay, and so what does that do? Well, it spans this gap between our predictions, our satellite and tide gauge records, and then these longer term, 100 million year records or hundreds of thousands of year records with coral data and that kind of thing. And so it fills this really nice gap, but it's also high resolution. So that's another thing that makes it very important. But why use salt marshes? Why are they any better than, I don't know, microatolls or any other given sea level indicator? Well, the distribution of salt marshes is intrinsically linked to sea level, right? They're only there because the sea is there, the ocean is there, right? The duration and frequency of saltwater inundation defines what species and what marsh grasses actually occupy the area. Okay, so, and one of the things that occupies the area is a thing called, little beasts called foraminifera, or bugs, right? Single-celled marine organism, very abundant in nature, in a lot of locations, generally very abundant in salt marshes, and they're amongst the best sea level indicators because they are very highly impacted by this duration and frequency of tidal inundation. So different that if you were in a high marsh environment, you would have a very different assemblage than a low marsh environment. And you can actually use that vertical distribution of the assemblage to tell you something about where you are relative to sea level, which is exactly what we're going to do. And the other thing that salt marshes tend to have, depending on the location you're going to, is they can have thick sequences of salt marsh peat, which are basically an archive of what sea level has been doing over time. Okay, so these are the things I'm going to take advantage of. take advantage of. And I'll show you how we do this. So one of the methods is that one of the most important things is to understand what the distribution of these forams is in the modern environment. That's intrinsic to us being able to estimate what the past elevations were. Okay, so it's key to go and get a basically transects of foraminifera across the salt marshes from the upland, where there's no foraminifera, all the way down into the lowest part of the intertidal zone, even into some of the channels or into the offshore. These distributions of species are highly tied to tide levels. Okay, so certain species are only going to live between highest astronomical tide and, say, mean high water. And that's going to be able, if we find those species in the fossil record, we're actually going to be able to tie an elevation to where they occupy in the salt marsh. And that's what I mean by being able to tell where sea level was. Okay, so we're going to use this data set of these modern distributions to actually predict where past used to be. And we do that by a paleoenvironmental modeling technique that I'm not really going to talk about today, but kind of just briefly go over it. So we use that big data set, right? We find these fossil organisms all through these cores. We use those assemblages to estimate, we use those modern assemblages to estimate that paleo sea level elevation. Okay, then we also take, we use carbon, radiocarbon to actually give a date to that sample. Okay, and the first step is, I'll go back one slide. The first step in this process is to define the relationship of a sea level indicator to a tide level in the modern environment. Okay, so that establishes where they are today relative to sea level. Then we find the assemblages in the paleo deposits, okay, and we use that data set from the modern to actually predict where that sea level used to be from the fossil record. So that relative sea level is calculated by subtracting the tide level, okay, from the elevation of a dated sample. Okay, so important in all this is, very important to all this, is altitude and age attributes. Right? It's very key to have the highest resolution altitude estimates of where you are in terms of depth and elevation and known datums. Okay, and it's also very important to have some of the highest resolution chronology or age control you can possibly get. Luckily, in a lot of the marshes we work in, there is Juncus or Marianus, which has very, very nice rhizomes, and they tend to be well preserved in the records. And so we can actually date those rhizomes and get really accurate, kind of plus or minus 15 to 20 year radiocarbon uncertainties. In the upper part of the record, we use things like lead-210, cesium, pollen chronohorizons, calibom, post-bomb, mercury in some places as indicators for chronological control. In terms of the altitude, we use things like an RTK and datums in order to get our elevation and our altitude data down to about plus or minus a millimeter. So why Florida? Why on earth would I pick Florida? Well, as I mentioned earlier, it's kind of at that toe end of the forebulge, and we're not exactly sure how far the forebulge goes to the south. We know that the data, we have ample data pretty much until you get into southern South Carolina, and then Florida, there seems to kind of be a data gap. Okay, and so that's really important because we don't know how much farther basically the isostatic effect is impacting to the south. So here's our locations in northern Florida and then in northwest Florida. And there's basically no valid sea level index points. And I'll explain what an index point is in a second. But just so you know, this is just the ice sheet extent, kind of at the LGM. The principal domes are identified here. And basically, one of the images you're going to see is the distance from Churchill, Manitoba to the sites in Florida. Okay, and that's going to be displayed basically in a latitudinal display, and it's going to show you the impact of GIA as you go away from that ice sheet. So this is, you're probably not going to be able to see this, you don't really need to, but there's no sea level index points in Florida, valid sea level index points. This is a database that a colleague of mine, Simon Engelhardt, developed in a paper in geology. And basically this is showing all the possible sea level index points all the way from eastern Maine down into southern South Carolina. Okay, and you can see that some of them are quite sparse, some of them are very well developed, right, in northern North Carolina. Some of the ones in Massachusetts are very, very well developed. But we start getting these we have gaps, right? We have gaps, and then we have a massive gap, right? We don't even have a table here for Georgia or Florida. Okay, so we got to make a table. We got to make a graph for Georgia, for Florida. So in Simon's paper, he actually looked at what was the GIA variability, that glacial isostatic variability, as you went from north to south along the Atlantic coast. Okay, and so basically here are these red dots. Okay, that's the variability in millimeters per year. So in Maine and New Hampshire, it's around 0.7, 0.8. Right? In Delaware, you have in New Jersey, 1.8 millimeters per year. Okay, down here in South Carolina, about 0.7. Okay, and that's basically the trace of those points as you go away from the ice sheet. So Churchill, Manitoba would be over here, and this would be down toward Florida. Okay, so our spots in Florida are actually going to fill this end, this toe end of that rebound process. Okay? The other thing you're actually going to notice from this map is that it's color-coded. The dark greens mean you have a high number of index points in those states. The light means you have none, right? So almost as you go down the coast, you actually have less and less data points as you go south. I don't know, I guess just more people want to look at salt marshes in the north. Not the same anymore. So the reason we're doing this is, number one, to develop that geologic context to compare these future projections, right? These are the rates of sea level change over the past 4,000 years. And basically what you're going to see is they also change as you go down to the south, right? In Boston, we have 0.6. Down in Delaware, 1.2 plus or minus 0.2 millimeters per year. The Outer Banks, around 1 millimeter per year of our relative sea level rise since 4,000 years ago. Okay, but what does that do when we get to the south? What does that look like, that background context? What's happening? Okay. The other thing that is now quite popular is these Earth ice models, or GIA models. A couple different groups are producing them, and they are basically projections. They can back project into the past to reconstruct what glacial isostatic rebound has done through time, but also they're used to help project the future changes, right? They're used because you have to basically decontaminate those records for any glacial isostatic movement, okay, to actually find out what is changing in terms of the eustatic part of sea level. And in order to validate any of these models, you need data, right? You can't turn all these knobs and just hope you're right? You actually have to validate it with some data. And so we've really been sought after by some of the groups to actually come up with longer records that have better constraints to actually compare to the data and show whether the data is valid, or whether the models are actually valid. And so we're working with Dick Peltier up at the University of Toronto to do some of that. Okay, so are the present rates unique? Right? Are these projections that we're seeing over the last couple hundred years, are they unique to any changes we've seen before? Are humans actually impacting sea level? Hopefully we'll find out. Recent accelerations, if you were to compare tide gauge relative sea level in millimeters per year, comparison to late Holocene relative sea level records, you can see that we have a plus 1 millimeter, right, plus 2 millimeters per year differences in certain areas, right? So these tide gauge records are showing that we are accelerating faster than we were in the past. Okay, well, what's Florida doing? We can't put a dot on there for Florida yet. So the Northeast study is in a location on St. Mary's River. It basically is the border between Georgia and Florida on the eastern side. Here's St. Mary's River. Really nice acronym, STM, St. Mary's. It's pretty smart. One of our better ones, really. There's 2 different sites. You're going to see a record from a place called Boggy Creek, which is around a 2,000-year record. And then we have around 8,000-year record from the St. Mary's River area. So one of the things I said in that method development, right, we developed this data set of the modern forems, right, and their relationship to sea level. Okay, and so here's an example. On the top we have, I think I have a laser here. On the top we have basically elevation relative to mean tide level as you go from the upland down into the tidal channel. Okay, we have an abundance of Amostuta inepta as you go across that transect. Milliamina, another kind of a low marsh organism, and then a few others. But you can see how some of them occupy certain areas of that elevation zone, okay, and die off, and then other ones replace it at different elevations. And so we're using that relationship to estimate these paleo elevations. Okay, and here's the stratigraphy for the salt marsh. We used the core from Site 2. It had a really nice, big, thick Juncus peat deposit of over about 1 meter. And lots of plant macrofossils, so we thought we'd really get a really well-dated section. This is what it looks like when the core is done. So basically, we counted every 2 centimeters. We counted the abundance of, or the assemblage of foraminifera in those samples. And then we took a number of radiocarbon dates all the way through this deposit. And basically what you're able to do is reconstruct where sea level used to be. Okay, and so we got about a 2,500-year record. Okay, and here we go. This is our record right here. We have years AD from -600 all the way to 2010. Up here is our reconstructed sea level, relative sea level record to do with recent relative sea level in meters. Okay, on top of this is a zoom in of this box, which is actually the tide gauge at Ferdinanda Beach, which is around 7 kilometers east. Okay, and it shows about a 2 millimeter per year a rate of relative sea level rise rate. Okay, and what you notice here is this is extremely straight. It's the simplest sea level reconstruction I've ever seen. It's almost boring. Right, you can just draw a straight line through it. I don't even need to do statistics. Right? I mean, it's basically a straight line. And so when you actually take the rate through this straight part, you can actually plot it right through time. The rate of relative sea level rise over this time period is basically bang on about 0.4 millimeters per year for basically 2,000 years. Okay, until this more recent onset of acceleration. So basically what you can do is you can take this and subtract it from that. And that's going to give you your sea level reconstruction instead of relative sea level reconstruction. Okay, so this is actually what's happening when we take away the glacial isostatic part. So this is the water part. So you can see it's really, really straight until this recent acceleration in around somewhere in the 1800s. Okay, so we know we have about a 2,500-year record. Our background rate, which we equivalent to basically as being GIA, related to this glacial isostatic rebound, okay, of about 0.4 millimeters per year. And we have an onset of that's recent acceleration that we dated to approximately 1870 to 1900. Okay, so that anthropogenic influence of accelerated sea level rise is around 1870 to about 1900. And it jumps up to about 1.6 millimeters per year instead of 0.4. Okay, so it's a big jump. We're having a big impact on sea level. Okay, so then if we go back to that recent acceleration, right, where we were looking at the late Holocene relative sea level rise versus these tide gauge records, we can actually plot Florida on here now. Okay, and we can see that we have, we're not out of the normal. We basically have a big, probably one of the biggest differences between the late Holocene and the modern, though, relative to the other locations. Okay, so that's something we did not know. It also was not expected, really. Now if we move to the longer core at the very similar site, we basically have a sequence of basal peat cores. So we basically core down until we hit the basal sand deposits across this whole paleo surface. And we've got about 30 different cores along this surface, basically here. And the nice thing about these basal peat records is there's no compaction of the peat that's right over top of the sand. And so you don't have to worry about auto-compaction of all that stuff that's accumulating above the peat. It's not actually forcing it deeper, okay, than it really is supposed to be. And so that's what's nice about the basal peat records, is you don't have auto-compaction. And so basically we counted the distribution of forams all through the cores and then basically recreated the same thing in terms of these records. Here's just an example of one of those records, what they look like. You basically have this basal sand deposit, usually quite a sharp contact, and then this really nice Juncus peat deposit. And then you look in them, there's always no forams in this sand deposit, right? Obviously being a land deposit. And then you start to get our freshwater deposit, and then you start to get the accumulation of these forams indicating when sea level kind of first intersects with that piece of land. Okay, and so you use that intersection, you date it, and then you're able to get a sea level index point. A sea level index point has a couple of requirements, right? You need to know the elevation of the point. You need to know the date of the point, right? So radiocarbon date or some age attribute. And you need to know its relationship of the proxy to sea level. Okay, so you have to have a quantitatively determined relationship to sea level, which these assemblages of foraminifera do. And that's how you decide whether or not you have a valid sea level index point or not. So this long record goes back approximately 8,000 years. And you can see we have a pretty sharp rate of rise in the middle Holocene from about 0.1 or 0.8 to 1 millimeter per year. Then again, we have that around 0.4 millimeter per year rise through the kind of the later part of the Holocene, really from 4,000 years, recent acceleration when we jump up to about 2 millimeters per year. Okay? And so basically these boxes are incorporating all the uncertainties that they're incorporating all the uncertainties you actually might get. And so the uncertainties this way in the box are the age, right, the uncertainty in the actual radiocarbon date. Okay, the uncertainties this way are the errors or uncertainties you would get with estimating that elevation, right? And those include coring angles, those include potentials for ranges in tidal frame or differences in tidal range over time. They incorporate things like just the error in the RTK process and getting a datum. Okay, so they incorporate all those different errors. The different colors, the base of basal ones are the ones that are right on that basal peak contact above the sand, are in blue. The basal ones are a couple, they're not exactly base of basal. They may be 20 centimeters above that sand contact. So they're not as potentially as valuable or as accurate. You can have freshwater limiting dates. Then we have our other site, which is we've just placed in green, which was that 2,500 year record on top of this St. Mary's record. Okay, and so when we look at them all together, we can actually compare this record to those GIA predictions done by Peltier. And he has a couple of iterations of these predictions. I think we compared to ICE 5G and ICE 6G, including rotational feedback and not including rotational feedback of the whole Earth process. And basically what we see is we have pretty good alignment between the data, right, and these glacial isostatic projections or models, but then it really starts to fall apart about 4,000 years ago, right? We have a really divergence between the data and these models. And this is actually true as you go up the coast. The whole section of the coast that we knew didn't match, the models did not match the data. Okay, so at first, all the modelers thought, well, the data people aren't getting it right. And I'm like, dude, come on. I'm like, maybe some of the knobs aren't being twisted in the right direction, or things aren't as homogeneous as you'd like them to be, right? Maybe you don't know the exact thickness of the crust and the lithosphere in each location, and maybe that things are laterally heterogeneous in different directions. And so there's a lot of, not really calling of names, a lot of tossing the ball back and forth of responsibility and that sort of thing. And but what's great is that the biggest issue was that we knew they worked in the Caribbean. The models and the data work in the Caribbean. And they work pretty well up in Maine. Okay, but it's this middle part of it's the mid-Atlantic down to Florida that basically there's offset as soon as you get past about 3,000, 4,000 years.
Excuse me.
Yes? Oops.
You're concerned about the most recent 1,000 years? All of the dots are outside the error bar for all of the models there, too.
Yeah, it looks like it's sitting a little low.
Not just the tail end of it.
Yeah, right. You can see there's also no uncertainties on the model.
Well, Dick doesn't allow that.
Yeah, right. So I give a little bit of leeway for that part. But anyway, so if you're actually to compare southern Maine, right, and St. Croix, okay, to northern Florida and northern North Carolina. Okay, and so immediately, if you look at it a little bit with some fuzzy eyes and have another sip of your beer maybe, You can see that, in general, Maine's a pretty good fit with at least ice 5G. Okay. Northern North Carolina, it's a pretty good fit back into about maybe 6,000 years, and then it just goes off, right? Just totally goes off the road. Another concern here is that it's actually sea level is actually going to go between this point and this terrestrial limiting date and these marine limiting points. So actually sea level is going to probably run somewhere through here. So actually, these are probably starting to be wrong somewhere about 4,000 years. Okay, as we go to northeast Florida, we have an okay, as we said, or as I said, we have an okay fit in the last until about 4,000 years, and then it starts to just be really bad. And then back in the Caribbean, we have a very good fit between the coral data and the models, but also these uncertainties are much larger because the coral has inherently larger uncertainties in terms of where it can live in the water column. So when we actually look at these, right, if we were to look at the ICE 5G model, okay, and we were to compare the rates of relative sea level from 8,000 to 4,000 years versus the rates of relative sea level from 4,000 years to just before the acceleration, okay, we can see that the green dots are the models of the different states. Okay, the data is in the blue dots. So, for example, here's the model of Florida. Okay, that's where it's modeled to be. The data says we're down here. Okay, so you can see how offset those two things are, right? And they're mostly offset in the older record, right? They actually almost fit in the more recent record, in that late Holocene record. And this is just comparing the ICE 6G model versus the data. And again, Florida looks like it fits pretty well with the late Holocene record, but again, in that early Holocene record, it just is totally off its in terms of predicting, in terms of making those predictions with any precision. So now we're going to jump from this northeast Florida record, and we're going to jump into the panhandle of Florida, basically, to a location called Lagrange Bayou in Choctawhatchee Bay. And what's interesting is, we kind of expected they're pretty close in latitude, these two locations. We kind of expected them to show likely similar rates of isostatic response. Okay, and so one of the things we wanted to do is we actually wanted to test that, because really people are mostly developing those records along the East Coast, and we didn't really know what was going to happen once we got into the Gulf. So the Northwest Florida, this is just the location here. We have this really nice, kind of a cute marsh, nice and narrow, not too far to walk through, only a few alligators here and there. So we got a nice little record here. I actually have a master's student on this right now as part of her, as her project. So it's actually, this is all really preliminary data, so no heckling. So one of the things about the Gulf, it's very different from the East Coast, right? We don't actually have, there have been sea level records that have been developed on the Gulf side. Okay, but there's a variety of kind of reconstructions that have been developed. Okay, and so some of them suggest oscillations in sea level where you've potentially had sea level above present in the Holocene. Some suggest just a kind of basically a gradual or pretty fast rise in sea level, and then a kind of slowing down of sea level as you get into the later Holocene. Okay, and so basically presently all the Northwest Florida data really suffers from kind of a sparse data points in terms of the records that they've developed, where they're tying together dots and kind of interpreting between dots. Okay, there's poor chronological control. No offense to people who have done them. A lot of them were done just a long time ago, and we've advanced in those methodologies. Some of them just don't have great elevation control. There's no quantitative indicative meaning with what they're actually using to indicate where sea level was. Okay, so the proxy they're using doesn't have a good relationship to sea level in the first place. So, right, so then the resulting reconstructions may not be a good estimate of where sea level was. Right, and we know there's this previous discrepancies between these kind of two groups of records where we've estimated either oscillations in sea level or this kind of monotonic rise. Okay, so we actually used a combination of those basal peaks that are right above that that basal sand contact, and we also used a long peak core, just to actually kind of, well, we're actually going to test compaction. We haven't done that step quite yet, but That was kind of the goal in this situation. And so we have about a 2.5 meter record of Juncus peat, which is really nice, has some nice plant macrofossils to date. We took a modern distribution as well at this site and used it to estimate this paleo elevations of sea level. This is just an example to show you what these sections look like. Here's that basal sand contact, okay, and then here's the salt marsh peat overlying it. What you would do is you would take samples all the way through here, determine whether they had forams or not. Right, the first time you find forams, you would then try and get a date as close to that position as you possibly could. And that would give you this indicative, this index point. Okay, and so that's what these records are developed on. This is that modern distribution of forams to build up that modern data set to make those estimates in terms of paleo elevation. You can see here as you go from the upland at station 1 down into the tidal channel at station 12, we obviously have an increase in salinity, right? And we have increases and decreases of certain assemblages or groups of foraminifera, which is exactly what we want. If they were all the same all the way through, right, we'd have a kind of not a great proxy. So this is our preliminary fossil reconstruction. I just got the dates like earlier this week. So I haven't fully digested this yet, and maybe you guys can help me out, but basically these are our cesium and lead-210 age chronologies. The green points, the green sample points are index points from that long core, okay, and the blue sample points, and the blue sample points are basal peat, the basal peat records, okay. And so you can see if you could draw a line this way, you could kind of draw a line this way. So we definitely need to get some more dates down here is the first thing that I decided. Okay, so what the data does initially show, and these are calibrated years from present back to around 6,000 years. Okay, and here's depth on the left. And initial data basically shows that if you actually take a line basically even just to here in this later Holocene period, kind of running all the way through these points right here, you get a rate of about 0.6, okay, or 0.56 millimeters per year, right? And if you remember from that northeast site, the rate was 0.4. Okay, so this site is actually, there's more rebound associated with this site, right? There's actually more subsidence associated with the receding ice sheet or the forebulge collapse. Okay, but we also do notice that we likely have a continuous relative sea level rise with no high stands, right? We're not seeing giant peaks up here or anywhere here. You could maybe claim a still stand, but at least no high stands for right now. Obviously, this record needs a lot more index points. We're planning on submitting a lot more dates for this record to kind of fill it out. But there's a couple things that we can actually kind of come home and say at the very end here. Oh, sorry, I forgot about this part. So what we wanted to do is we know that we actually developed, there are already records developed in Gulf. One of these is from Donnelly and Geosan in 2006, and he kind of summarized Tor Tornquist's work, Staper, Wright. And basically this is the record that was pulled out of that journal, and it goes from present back to around 8,000 years, and again we have depth over here. And you can see that the white open boxes are actually Tor's data from in the Mississippi Delta area, and then the black boxes are Wright's data, okay? And we can see our data kind of smattered on top of that, which seems to kind of work out until about 3,000 years, despite there's this problem and this problem. But again, we need to start filling in this record. We have quite a few temporal gaps in the record, and then some uncertainties in which way the record should go, really. So that's something to do for the future. But what is that then? We're coming back to the end. Where does that put our sites on this map of showing where you are in terms of your rebound isostatic deformation? Okay, and so here we have the current rate of GIA subsidence in millimeters per year. Okay, and here's 0.2 all the way to 1.6. Okay, and here's the distance from the center of the ice dome at its maximum, which is estimated to be around Churchill, Manitoba. Okay, and so basically when we plot this, we see that we have Northeast Florida plots, it's a little bit further away actually from the center of the mass at around oh, that's not even in the right place. Okay, so that one's supposed to be at around 0.4, and this should be at around 0.5, 5.5. So actually should shift up a little bit. Maybe it's just the way I'm looking at them. Anyway, but what we did develop is we have about 50 sea level index points for Florida, where previously we had no valid sea level index points, so that's awesome. Okay, over the last 8,000 years, we think that we're okay with saying we have relative sea level rise through time. We don't think we have any oscillations in sea level over this time frame. We also don't think there's any high stands in this time. We have a late Holocene relative sea level rate of rise of about 0.4 millimeters per year in the northeast site over here, and then about 0.56 over here in the Panhandle site. And this recent acceleration that you actually see in the tide gauge record and in the proxy record is unique to the last 8,000 years. At no point in those proxy records does it actually increase at a rate, as it accelerating at such a rate. Okay, so that's important to know. So maybe we are impacting sea level. We also have continued misfit with the GIA models. Okay, so there's something wrong. Now that we're building up these large amounts of data, is it still the data that's wrong? You know, maybe it's the modeling. Okay, and so all this is going into basically, you know, building up these really great records and kind of finding that toe end of the isostatic response of the continent. I believe that is basically all I have to say. So thanks.
Awesome. Thanks, Andrea.
Oh,
Go ahead and finish yours.
ask away. Sorry, I was really thirsty all of a sudden.
Just two questions. One is the error bars on that 0.4 versus 0.55 GIA.
Right.
What is it roughly? Is it 0.1 millimeters per year?
So the uncertainties in our actual estimates are around 12 centimeters. Okay, then when you back out the rate, it would equal, they would be outside of the error bars. They would be different. Okay. So it'd be about 0.04, sorry.
0.04,
yeah.
okay, about 10%.
Yeah.
Okay.
So yeah, the marsh estimates are generally between 8 and about, like this whole reconstruction process, generally fit anywhere from about 6 to 14%.
Okay. The next question is more about the technology we have at our hands today with GPS measuring vertical changes. Are these rates matching up with what we're seeing today?
Yeah. Have you ever gone and looked at a GPS array of vertical deformation?
Yeah, it's very noisy.
Yeah, it is a mess. So we tried that. We actually tried that for this Northeast Florida. We're just developing a paper right now about that, and we went and looked at some of the data, and we really just can't even. The uncertainties just they're too big.
When you look at the tide gauge records along West Florida and the east coast of Florida,
Right, very different.
no, they're actually quite consistent, and there is about a 0.1, 0.2 difference
Of the tilting,
which is consistent with what you're
right.
saying.
Well, I was just thinking of the tide gauges. If you looked on each side of Choctawhatchee Bay, those are completely different, those tide gauges.
Too close together.
Yeah.
And I can give you something about it later.
Okay, awesome. That'd be great. Yes.
I think you've got to be careful of making broad generalizations of broad geographical areas.
Okay.
The Caribbean is all behaving
Oh.
the same way. And I know you
Yeah.
didn't mean to say that, but
Yeah.
the Caribbean is enormously
No, yes,
different.
very tectonic.
And Florida is quite different than the rest of the U.S. Now, North Florida is very much like Georgia and South Carolina and whatnot.
Very
When
true.
you get down into the limestone bedrock, it's probably going to behave quite differently.
Yes.
Probably be a lot more stable, and probably be a very good place to get a lot of basal peat type environments. Instead of peats on sand, you got a peat on easing rock.
Yeah, the biggest problem with the rest of Florida is that you get into mangrove peat. And
Well,
mangrove
the
peat,
The Juncus goes down to here.
yeah, it goes down to about Daytona,
Mangrove
actually,
starts
yeah.
about here. The mangrove line starts about here.
Right.
The northern mangrove. So you're down onto the carbonate platform. But then you step over into where Tornquist worked.
Right.
It's a completely different ballgame.
Yeah.
You know, with the Mississippi River
Right.
and everything else. And so there are big geological differences, and you're trying to see very small differences in very small numbers in areas where there are big geological differences.
Mm-hmm. This is true. Sea level's complicated. Yeah, and I mean, one of the things we have been trying to work further down into Florida. Because I do think it's going to change.
We'll go to where Eric Wright did his work.
Right.
And get basal peaks there.
That's on the-
Interesting to see what you get.
We have people who are going to do that in the next couple of months, actually. With Ryan, I think with a project with Ryan. So who's here? Yeah.
So if we were able to define some real datum, and we can measure everything relative to that real datum, how would all the individual terms that go into relative sea level rise vary? And what sort of errors do we find with each one of those individual terms?
Right. Well, it also matters the time scale you're reconstructing over, because only some of them are going to be important, depending on that time scale. Right. So tectonics, not.
So if you just think about mass of water and the volume of the water versus the bulge going up and down,
Mm-hmm.
compaction, whatever. I'm kind of curious what the relative magnitudes are of all those individual contributions to relative sea level rise.
Right. So there have been people who have made estimates for how much is actually contributing, what percentage. And that's, I forget what that paper is, Mitrovica, maybe? And basically that it was, 40% of relative sea level is attributed to GIA, and 20% is attributed to glacial melt. And then that's now changed to really being 20% being GIA and 40 or 50% being glacial and ice sheet demise. Okay, so is that what you mean, or am I not?
Yeah.
Yeah, no, so people have made those estimates. But it's timescale, massively timescale dependent, especially like the thermosteric and.
A follow-up on Bob's
Yeah.
question, that is, one of the other major features of your climb from Maine to Florida is the thermal rate that you have there, right? So if there's any differential thermal expansion that's going on over those timescales, then that certainly is going to influence the balance.
Right, and if you think of where the misfit is with the model, it basically starts where the water starts to warm up, right? Where you get things like AMOC maybe playing into that, right? Current shifting north-south, where you get things like people have suggested maybe even the Orangeburg Fault. But when you actually deconstruct and figure out its movement over time, it really can't add much. But there's definitely been people starting to look into the thermosteric influence of just being in different parts next to the Gulf Stream and not really next to the Gulf Stream, basically.
That's what I was going to say. The big change is due to the Gulf Stream gradient, but that does go to the thermal because of the wind. The Gulf Stream is driven by the wind stress curl, so there is a possibility there.
And in the past, that strengthening and weakening of that current potentially with large donations of cold water, right, from the north.
I think it's all in the upper there. The Gulf Stream magnitude is much stronger than the AMOC effect. You have to change the AMOC at order 1 instead of a few percent.
Right, yeah.
So can you interpret what they're saying and you're saying so that when you compare it to the GIA model, it has this nice kink.
Right.
We just see this straight.
Right.
Are you saying, I mean,